Now coming to this induced response that we mentioned just now. The instrument essentially captures samples only where we have these unique spacings between the various different antennas, right? So we refer to this response as the point spread function. Some older folk may refer to this as the dirty beam, right? And you'll see that popping up in some older literature. And that is essentially just the response pattern of our sampling function, right? Remember that we capture only samples within this UV space. So mathematically, it is the Fourier transform of the sampling function. So that's all that's the definition of the PSF. So this effect can be seen across other instruments as well. For instance, if we look at the Hubble Space Telescope, on all strong stars, you'll actually see a cross-like pattern on the image, and that is Hubble's PSF. Now, that PSF is much more compact because essentially, there's much less structure to the mirrors and so forth in an optical instrument. However, for a radio interferometer, we're missing a lot of samples in the UV space. So our PSF is going to be much more pronounced. The more samples we have on the UV space, the better, right? So one way of doing this is to just add more and more antennas to the array. Well, that's a very expensive proposition. So we can see the effect that adding more and more antennas has to the response to a single point at the phase tracking center, which is also by definition then the PSF. So you can see if you have only a few antennas, we have very few spacings, right? So where the number of spacings is essentially just just about half the square of the number of antennas that we have in the system. Now, as we increase the number of antennas, the number of unique spacings that we have thus scales roughly quadratically. And we can see that if we have only a few spacings available within the UV space, we cannot really localize this, a single source very well. It can be pretty much anywhere on the image, as you can see on the left-hand side there. Now, as we increase the number of available unique spacings, we can see that an instantaneous view of the sky sort of starts to at least localize the source pretty decently well once we start going into the mid-20s for a number of antennas. Now, as I said, of course, building more and more antennas is a very expensive proposition. So are there any other ways that you can think of about how we can increase the number of samples that we have in the UV space? Well, apart from building more antennas, we can rely on the fact that we're taking spatial coherency projection measurements, right? The word projection here, right? So as the Earth rotates underneath the sky, the physical orientation of the baseline changes with respect to the source vector, right? So now these will take different spatial frequency samples for us. So by allowing the sky to rotate for an extended period of time, so hours, we can steadily build up more and more unique samples within this UV space. Now, for a snapshot image, so for let's say 5 minutes or so, we can see that the instantaneous coverage gives us rough localization. There's still a lot of extended side lobe structure to our response function here. But as we start observing for longer and longer and longer, the source is localized better, right? So after 12 hours, we get very low side lobe levels and very good localization of the source, right? So any other way of of increasing the number of samples in the UV space? Well, remember that in the visibility section, we discussed the fact that the UV coordinates themselves are a function of wavelength, right? So we measure our UV distance in wavelengths. So by observing more, a larger bandwidth, we can actually increase the number of samples, right? Because it will scale out radially in this space. So you can see that for a very fine bandwidth, with only a few channels in it, we can see that the samples are just points on this UV space. Whereas if we increase our bandwidth considerably, then we start capturing more and more samples along the radial direction in this UV space. So that is another way of increasing the number of samples in this space. And if we couple that with this Earth synthesis way of making images, we can pretty much get a very good coverage of the UV space. So let's consider for a moment the effect of different length spacings. So let's look at the VLA in its deconfiguration here. The PSF, so the instrumental response to a point source, is indicated here in the middle. So it's as you can see, it's very broad, right? Because as we said, if we have an array that has only short spacings in it and no long spacings, the response to that will be biased towards broad scale structure, right? And that's exactly what we're seeing here. The instrument response here is selecting out only the broad scale features of Donald Duck, right? So this is why we see only broad scale features if we convolve this instrument response with Donald Duck. Now, let's look at the VLA-A configuration, where we've moved the antennas into distances up to, I think, about 36 kilometers apart. Now, this array is going to be biased towards the very fine scale structure in the sky. So you can, so this filter, we can think of the PSF then, will pick up all the lines and points and so forth of this image. And that's exactly what we're seeing, right? So it really depends on your science case which array configuration you want. If you're only interested in broad scale structures, you want to go with an array that has a lot of short spacings. Whereas if you want to do extragalactic work, you'll go to for an array that has very long spacings. And this is why we build these very large arrays. So the resolution of our instrument depends on the longest spacing. So that's only one section of imaging. Remember that our image is convolved, or all the structure in our image is convolved with the PSF, and the side lobes of this PSF needs to be removed if we want to have any chance of doing really detailed science with it. So, and this we refer to as the process of deconvolution. So imaging is about cleaning that dirty duck. Now, the most basic algorithm that's been there since time immemorial really is the Hochbaum algorithm. It essentially goes like this, right? So given a input dirty image, right? So an image that is convolved with the PSF, we go and peak find the brightest position in this image. We take the PSF, shift it to that position, subtract a fraction of that PSF out, so let's say 10% of the peak of the PSF, right? And that gives us a new residual image, right? So we can think of this as residual 1, where residual 0 will be the dirty image. At that subtracted position, we've recorded now the amount of flux that we've subtracted out, so 10% of that peak flux, right? And then unless we've reached some stopping criteria, so let's say we've defined the stopping criteria to be the peak is going to be, let's say, 10 times the noise of the RMS noise of the image. That's one stopping criterion, for instance. We go back and repeat this process, and therefore we gradually build up a model of the sky, right? Where the model consists just of these Dirac delta functions at the recorded positions and a residual, right? So as the residual goes down, we've gradually subtracted out all the true flux in the sky. Now, at the end of this process, we perform essentially a painting operation where we convolve with a Gaussian function that is fitted to the primary lobe of our point spread function. And this we refer to as the restored or cleaned image. Now, let's look at just a toy example here. So let's start with a true sky, right? That has these three sources in it with noise. Remember that we will always have noise on the interferometer, primarily because of the low noise amplifier, right? So even in the absence of any calibration errors, we will still have noise on the system. Now, as we said, the dirty map is the true sky distribution of sources convolved with the point spread function, right? And let's say our idealized point spread function for our interferometer looks like that image in the center there. Now, the dirty image is then this convolution between the two. Now, the goal is to get back to get a model that is close to the true sky model here, right? So what we do, we start off with the dirty image, as I said, and then we peak find and mark the positions of these peaks. And as we go down, our residual image starts to have fewer and fewer and fewer side lobes until it becomes, well, noise-like, right? I say noise-like because the noise itself is still convolved with the point spread function, so it's not quite Gaussian noise anymore. So if we started off with plugging in a true sky into this deconvolution algorithm, we get a deconvolved sky model as indicated on the right-hand side there, where you can see it has picked up a few of these noise peaks, but it has recovered a bit of flux for each of those real sources. So that's the goal of the algorithm. Now let's look at the real-life example. Here we've captured a relatively void field, so what's called the Deep 2 field with Meerkat. And you can see that for a 16 antenna array, so if we pick out only a few antennas within the array, the side lobe structure is quite pronounced, right? So you can see that if we convolve that PSF response into our image, the side lobes of these brighter AGNs within the field is very pronounced, and they actually wash out any of the fainter AGNs and star formation population that we would want to measure. So we would need to deconvolve this, right? And after deconvolution, in the way I've just described, we get an image, restored image on the right-hand side. So in this case, you can see all the faint emission is now visible, and that previously lied below this, the response on bright sources. All right. So, well, you could say this deconvolution algorithm is quite simple, and therefore it's also quite restricted, right? So the clean algorithm assumes that you essentially have a near empty patch of sky that you're trying to deconvolve, right? So, and that patch of sky further is dominated by just point sources, so unresolved sources. So it can deal with diffuse emission, but not really very well, right? So remember that our model is going to consist only of a bunch of Dirac functions, right? So it can only really suboptimally model diffuse patches of emission, because that diffuse emission has a bit of coherent emission in it, right? So you can't just model that with just a bunch of points, right? As our telescopes and our instrumentation grow more sensitive, have wider fields of view, and we have these very core dense arrays, such as we have with Meerkat, for instance, then we are very sensitive to diffuse emission. So this is where this algorithm breaks down. Now, there are ways to mitigate for this and introduce more basis functions aside from the direct function, but in its most simplest form, most imagers still use a variation of the Ogbom algorithm. Now let's look at how we can bias our visibility measurements in a way such as to suit our science. So to do this, we assign weights, right? So we need to ask ourselves, for a given array such as, say, Meerkat, do we get a homogeneous density of these Fourier or spatial frequency measurements? Well, the answer really is no, right? Because if we consider Meerkat, for instance, about 70 to 75% of all the antennas in the array is located within just a 1 kilometer radius, and the array extends out to almost 8 kilometers. So it will definitely not give us a homogeneous measurement of this UV space. Well, could we perhaps adjust the weights we average all these visibilities with? Well, as I said, it depends on your science goal. Now, let's look at the two extremes here. In the first extreme, we are sensitivity optimal by just assigning unity to all the weights. So we take all the measurements as it stands with equal importance, right? This gives us something that's sensitivity optimal, right? We haven't thrown out any information here, but in this case, we are by far resolution suboptimal, right? Because for an array such as Meerkat, where there's a lot of samples in the middle of the UV space, that biases the array's resolution to broad scale structure. So we're going to be resolution suboptimal, right? Now, on the other end of the spectrum, we have what we call uniform weighting. And to get a uniform weighted image, we just take each of the visibility samples and we weigh it by the number of samples that is around it, right? So if we have a long baseline measurement, there is not a lot of measurements around it. So we're going to upweigh that measurement. And for a sample that's taken in with the core of the array, so the sample that lies within the center of the UV space, we are going to downweigh it because there's lots and lots of samples around it, right? So in this case, we drive our instrument to be somewhat resolution optimal. However, at this point, we've thrown out a lot of information and we've become sensitivity suboptimal. Now, it depends on your science case on which configuration you want to use. So if you want to do H1 science on nearby galaxies, for instance, then you'd want an array where the long spacings essentially has been thrown away because you only care about broad scale emission, right? For that, you will taper off the long spacings and you'll select something that's close to natural weighting, right? For extragalactic work, you want something that is more resolution optimal, because as you get more and more sensitivity, sources starts blending together and you want to be able to distinguish between different sources on the sky. So you would pick something that is more uniform weighted. Now, there is a compromise here. We call this Briggs weighting, so named after the late Daniel Briggs. So it provides us with a way to parameterize this weighting with a single parameter, right? It's just a sliding scale between uniform and natural weighting, where in most images, uniform weighting is around -2, and then natural weighting is around +2. In other images, such as the apes imager, it's slightly different. So that ranges from -5 to +5. But nonetheless, it doesn't really matter. It just provides us a way to slide between being sensitivity optimal and resolution optimal. Right. So you can see that if we flip between natural and uniform and Briggs weighting, so if Briggs weighting gives us something that is somewhere in the middle, and that's user defined. Now, coming to Meerkat, the Meerkat response function, so the PSF, is essentially a composition of two Gaussians. Why, you might ask? Well, the core of the array is essentially Gaussian distributed, right? So all the antennas are pseudo-random positions. That's roughly Gaussian. Then we have another distribution of antennas towards the edge of the array. Now this essentially is going to give you, in the Fourier transform, a Gaussian, a narrow Gaussian stacked on top of a bigger Gaussian, right? So if we go to a natural weighting here, and we equally weigh all the samples, then you'll see this kind of top hat structure, right? And that's really not desirable, because for any compact point source you have in the sky, if you don't deconvolve that properly, you'll still see broad scale stuff around it, right? Which you can confuse in certain circumstances, such as galaxy cluster sciences for broad scale emission. So this is really not great. So what we want to do is use Briggs weighting to select a resolution that is perhaps somewhat more sensitivity suboptimal, but it at least doesn't have this broad scale flanks to it. So a Briggs weighting in the -2 to +2 scale that we typically use for Meerkat is about -0.3 to about 0. So that gives us a crafted PSF response where the side lobe is washed out for the most part. It's nice and flat, and it gives us a Gaussian-like response in the center.